sections. So let's start with a definition. We already know all about slope and different forms of the equation of the line. So we're going to say two lines are called parallel if they do not intersect. One thing that I just want to be clear about is when we talk about lines in this course, everything that we're doing takes place in the XY plane. I think on the first day of the semester, we talked about the XY plane, also known as the Cartesian plane. So we're basically doing two-dimensional graphs. If you go to 3 dimensions, things can be a little bit different. But if we're in the XY plane, two-dimensional pictures, two lines are parallel if they do not intersect. So I'll draw a couple of quick examples. Here's an XY plane. I'll draw two lines that do not intersect. Well, how about this line and this line? They're not touching. They're not touching each other, and it looks like they never will. They're kind of the same distance apart all along the length of the line. It looks like as we keep going down and left, they're never going to touch. As we keep going up and right, they're never going to touch. So I'll say that those two lines are parallel. And one feature of parallel lines that we can start to see, even just from this first picture, is they have the same slope. I'm going to write that underneath here, same slope. Because remember we said that you could think of slope as for every 1 unit you go over, how many units do you go up? I didn't really label the x-axis and y-axis numbers for scale, but we could still see that if we go over a little bit and up a certain amount, it's the same amount for both of them. So same slope. Another example of parallel lines, making a smaller picture up here. There's another XY plane. Maybe this one I will label some things for scale, like, why not? 1, 2, 3. 1, 2, 3. How about if we had this line and this line? They're both horizontal. Two horizontal lines. They are also parallel. They will never intersect. They also have the same slope. Remember last time we said that horizontal lines have a slope of 0. So these both have a slope of 0. There's one other case where two lines could be parallel. How about this line, vertical, and this line, which is also vertical? They don't have to be super close to each other. They can be spread out a little bit. But two vertical lines look like they are never going to intersect, right? So I'm going to say that these are parallel lines. They are parallel to each other. Do they have the same slope? I guess in the other pictures I said same slope. Is it fair to say that two vertical lines have the same slope? Well, not really. I'm going to say both have undefined slope. They both share that in common. It would seem a little weird to say that their slopes are equal because they don't really have a slope. But we'll say they both have undefined slope. Let's do another example. Let's do one that has an actual equation. So example, let's say we're given y equals 2x plus 3. We'll think about this line. That's in y equals mx plus b form, right? Slope-intercept form that we talked about in the previous lesson. So this is the slope, and this is the y-intercept, right? So if we wanted to draw y equals 2x plus 3, we could draw that. And then we'll think about what lines are going to be parallel to this. Let's draw it first. All right, well, y-intercept is 3, so I'll draw a dot at 3. And the slope is 2, so for every 1 unit I go to the right, I should go 2 units up. So like the point 1 comma 5 is up there. Also, for every 1 unit I go left, we go 2 units down, right? So you can draw the line like this. This is a good picture of y equals 2x plus 3. So what I want to say off to the side is any line parallel to this must be y equals mx plus b with the same slope. It has to have a slope of 2. So the only thing that can really be different about it is the y-intercept, like the b. B could be different. So y equals 2x. How about y equals 2x plus 1? Here, let's label some of this stuff. So that I'm about to draw more stuff on this picture so that we don't lose track. Let's remember that this is y equals 2x plus 3. I'm going to draw y equals 2x plus 1. That has a y-intercept of 1 and the same slope. Like that. That's my y equals 2x plus 1. It has a different b, but it has the same m. And yeah, those lines will never intersect. B could also be negative. Let's draw one more on this picture. How about we go with, what if b is negative 3? So y equals 2x minus 3. That would cross down here at minus 3. It would have a slope of 2, so it would go through this point and this point. That's my y equals 2x minus 3. So all 3 of these lines are parallel to each other. They all have the same slope, and they will all never touch each other. They never intersect each other. So if you have a question about parallel lines, I guess the most important thing to remember is that parallel lines have the same slope, unless they're vertical. If they're vertical, then we just say they both have undefined slope. We have another definition for this section. Two lines are perpendicular if they intersect at a right angle, meaning they intersect at a 90-degree angle. We haven't really talked about angles in this class. It feels like what we're talking about in this lesson could also be discussed in a geometry class. Like in a geometry class, you might talk about parallel, perpendicular, right angles, 90 degrees. It can kind of be thought of in terms of functions and algebra, or it can be thought of as geometry. Two different perspectives. Let's draw some pictures here. I think it's a very visual thing. We want to draw pictures. So what do perpendicular lines look like? That's kind of our first question. And then what does it have to do with slope? That's going to be our second question. All right, so here's an example of two lines that are perpendicular. How about this line and this line? Making a big X across the plane. Oh, here's a question. What slope do you think those two lines have? You can probably figure that out. Well, first of all, I'm saying that these two, they intersect. They definitely intersect right here at the origin. And they're intersecting at a 90-degree angle. Sometimes for a 90-degree angle, we put like a little box there. Put it like here maybe to indicate 90 degrees. This first one has a slope of 1, and the one down here has a slope of -1. So that's an example of two lines that are perpendicular. For the next example of perpendicular lines, let's go with something that's not as simple. I have two lines in mind here. Let's see. I'm going to draw a line that has a y-intercept of -4, also an x-intercept of 2. This is my first line, and my second line, I've got x-intercept of 2 and a y-intercept of 1. All right, so it turns out that those two lines, they intersect in one place, and they do so with a 90-degree angle. So this angle right here is 90 degrees. Make kind of a nice square shape there, like the corner of a rectangle. What slope do these two lines have? Can we tell by looking at the picture? Looking at the first line that I drew, it looks like for every 1 unit I go over, I go 2 units up. 1 unit over, 2 units up. So this has a slope of 2. How about my other one? For every 1 unit over, I'm going half of a unit down. 1 unit over, half a unit down. So this actually has a slope of -1/2. Negative because we're going downward. So what do you think the relation is between the slope of two lines that are perpendicular? Well, we're going to establish a general rule in a minute or two. But, you know, we had a 1 and a -1. That's perpendicular. We have a 2 and a -1/2. That's perpendicular. There's one other case I want to show you first. One other case is, what if the lines are horizontal and vertical? So I'm going to do this horizontal line here and this vertical line here. Look at that. That horizontal line and that vertical line, they look like they intersect at a 90-degree angle. So yes, they are perpendicular to each other. Can we say anything about the slope of these two lines? Well, the horizontal one has a slope of 0. We know that for horizontal lines. The vertical one has a slope undefined. So we're trying to think about establishing a general rule for like how the slopes of perpendicular lines are related to each other. But it feels like this, the horizontal and vertical one, that might just turn out to be a special case. That's just kind of its own thing. Vertical lines are a little unusual when we talk about slope. Okay, so let's state our general rule. In general, the pattern that we're getting here. Let's say for non-vertical lines. If we're given a slope of C over D, a perpendicular line has slope negative D over C. That's the relation here. In fact, it's flipped. I guess you could say it's a reciprocal. Here, I'll write this. It is the negative reciprocal. Sort of flipped in two different senses. What I mean by that is the sign is flipped, plus or minus, and also the numerator and denominator are flipped, top to bottom. So yeah, this makes sense if we look at our first two examples. Slope of 2, you take the negative reciprocal. It even works with the first example. Take a 1 and take the negative reciprocal. Even if it's not a fraction, it still works. I mean, 2 could be thought of as 2 over 1. We usually wouldn't write it that way, but it can be thought of as 2 over 1. The reciprocal is 1 over 2. So let's do an example problem. I'm going to give you a problem with 2 parts, and I'm going to ask you to try this. Find an equation of the line through 1, 1 and 4, 3. And I'm going to say write in slope-intercept form. There's also going to be a second part, slope-intercept form. By the way, part A is really a question that I could have asked you in the previous section. Part B is going to be the new part. Part B, find a line passing through -1, 2 that is perpendicular to the line from part A. Write in slope-intercept form. So I'd like you to take a couple of minutes, pause the video, and work on this, and then check back with me. All right, so I need a fresh sheet of paper. I'm probably going to have to move the question away, but I think we've all got the question down. Let's talk about part A. Part A. So we want to find an equation through those 2 points. I think the first thing we should do is find the slope. We can't really find the slope-intercept form unless we find the slope. So the slope is 3 minus 1 over 4 minus 1, which simplifies to 2/3. Even though the problem says slope-intercept form, I'm going to start with point-slope form because remember, sometimes it's convenient to start with that. And then we'll get it into the correct form after we find this. So we can use either of the 2 points that were given. We were given 1, 1 and 4, 3. It turns out that you could use either point. I'm going to use the 1, 1 because that sounds easier. And put in the slope that we found. So these are both still point-slope form. I'd like to get this into slope-intercept form, which is y equals mx plus b. To get this to y equals mx plus b, we want to get y by itself. We also want to distribute what's on the right-hand side. So I'm going to add 1 to both sides. I'm also going to distribute the 2/3. 2/3 x minus 2/3, and then I'm adding the 1 to bring it over. And this simplifies to y equals 2/3 x plus 1/3. And this is slope-intercept. And that's the answer to part A. Like I said, part A is something that really comes from the previous section. Part B is the one that's really for this section about perpendicular lines. So in part B, we were given a point, and we're told that we want to make a line that's perpendicular to the one from part A. Well, we know what the slope should be, right? The slope should be the negative reciprocal of 2/3. That's going to be negative 3/2. And we want a line that passes through -1, 2. So we have everything we need because -3/2, that's going to be the slope, so that's m. And then we have x1 and x2, oh, sorry, not x2, y1. So we have x1, y1, and m. We can find an equation of this. Let's do this the same way that we did part A. We're going to find point-slope form first. But using these pieces, using this x1, y1, and this m, so y minus 2 equals -3/2, x plus 1. Let's distribute the -3/2. X minus 3/2. And now I'll add 2 to both sides. So y equals -3/2 x. Okay, what happens when you add 2 to -3/2? You get plus 1/2. And that is exactly the form that we wanted. So that's the final answer. Okay, so that problem combines some things from the previous section and this one. You could get a problem like this that involves perpendicular lines, and in that case, the slope should be the negative reciprocal. You could also get a problem similar to this that might ask you to do a parallel line. And I guess if it's a parallel line, it's a little bit easier. Just remember that parallel lines have to have the same slope. So you don't have to do negative reciprocal in that case. Just pay attention to whether it's asking you for parallel or perpendicular. Don't get them mixed up. We've got one more thing to talk about for this section, because this section is supposed to be more about slope. And one thing that we should address before we move on from slope is that slope measures a rate of change. You know, we say that it's y2 minus y1 over x2 minus x1. But remember, when we first had a definition of slope in a previous lesson, I said that you could think of it as the change in y over the change in x. How much did y change when you went from one point to the next? How much did x change when you went from one point to the next? So it's a rate of how the function is changing. And I'm using the word function, and sometimes when we talk about functions, instead of calling it y, we might call it f of x. So how does this change if we call it f of x? Well, we're not going to say y1 and y2 anymore. We want to write it with f. We can say f of x2 minus f of x1. That is what goes up top, and the bottom is still the same, x2 minus x1. Now, is this really any different? It's kind of saying the same thing. It's just written with f of x notation instead of y's. F of x2 is the y coordinate that goes with x2. So it still works. It's still the same idea. I'll put a box around this as a formula, but I think if you remember the slope formula, you should be okay. And we use this to measure the average rate of change. I'm going to underline that. The average rate of change of f of x, of a function f of x. I'll show you an example. All right, let's do an example with an actual function formula. This is one type of problem that you might see. Find the average rate of change of the function f of x equals x squared from x1 equals 1 to x2 equals 2. And I'll do this one for us. I'm going to walk us through this. This should actually be pretty quick. I mean, really, we're just going to use that formula. M equals, we have x1 and x2 given to us. So let's say f of 2 minus f of 1 over 2 minus 1. In this case, for this problem, the function that we were given is x squared. So what is f of 2? F of 2 in this problem is 2 squared. What is f of 1? It's 1 squared. A different problem might have a different function. F of x equals x squared. You could have f of x equals x cubed. F of x equals something else. But for this one, it's just squaring these. So I do 2 squared. Let's move this. 2 squared up top is going to be 4. 1 squared is 1. On the bottom, 2 minus 1. So this simplifies to 3 over 1. 3 over 1 is 3. That's the answer. That's the average rate of change of this function from this x value to this x value. Now, before we finish up, I want to draw a picture and maybe explain to you, what does this 3 mean? What does the 3 represent? So visually, we answered the question visually. What does that 3 mean? We know what the graph looks like for f of x equals x squared. So let's draw a quick picture of it. I'm kind of focusing on quadrant 1 because I think that's where this is really taking place. Okay. Here's 1, 2, 3, 4. Okay, that's good enough. So what did we figure out? What is this 3? It feels like we calculated a slope, right? It almost feels like we did a slope. But remember, when we had a definition for slope, the definition of slope says we're talking about a straight line. This is not a straight line. This is a curve. So is it really fair to talk about slope of a curved line? Well, look at the numbers that we used. We really used 4, 1. We used 4 and 1 as the y values. We used 2 and 1 as the x values. We basically went from here to here. And we calculated the slope of a straight line between these 2 points. And for that straight line, we found that there was a slope of 3. But the actual function, f of x equals x squared, that I drew here, f of x equals x squared, it's not a straight line. So we can't really calculate the slope of a curved line, not exactly. But what we did calculate, the 3, it's still kind of telling us what the function is doing from x1 equals 1 to x2 equals 2. It's kind of like what's happening on this part of the function, what's happening on this interval. It is increasing with an average rate of 3. For the 1 unit that we go over, we go 3 units up. Okay, so that's why we talk about average rate of change. It's a little bit like slope, but it helps us with things that don't have to necessarily be straight lines. As a side note, the straight line that I drew, this blue line, if you can see in the video that that's a blue line, the straight line that I drew is called a secant line. It is a straight line that connects 2 points on a curve. Okay, so that's average rate of change. And that is the end of this lesson. So I'll just leave this for a moment in case you're still writing this.